Hello there, and welcome back to the course summary of EE2015 Electrical Circuits and Networks. So, in the last video, we just had a small overview of what the entire summary is going to be, what the course has got, or what the topics are, and now this will be the official start of the course content. So, basically, throughout the course, we'll be dealing with linear systems and some circuit elements. So that is what this video is going to be about. So let's start with linear systems. So what are linear systems? So basically, if there is a system that operates on a signal, basically, if we give it an input, say x1, it gives an output signal y1, and for an input signal x2, it gives an output y2. So if the system is fed with an input AX1 plus BX2, where A and B are constants, it should give an output of AY1 plus BY2 if it is a linear system. So the circuit elements that we are going to deal with, basically the inductors, capacitors, resistors, they are all linear elements. They follow linearity. And talking of the circuit elements, as we said, inductors, capacitors, resistors, and apart from these, voltage sources, current sources, and dependent sources are what we are going to deal with. So, for understanding the current and voltage characteristics across these circuit elements, one has to have a sign convention for the current and voltage across these systems, because as we go through this video, you'll realize why is it important to have a standardized system for measuring the voltage and current across these sources and elements. So let's see what these passive elements are. Basically, passive element is a one which does not generate or modify the nature of voltage or current. It can only dissipate, store, and release the stored energy. And yes, resistors, inductors, and capacitors, these are passive elements. They may need an external energy source to operate, but I'll reiterate on that again. They dissipate, store, and release the stored energy. They cannot generate or modify the nature of the energy, which is in the form of current and voltage. So let's start understanding what passive sign convention is. So yeah, so basically in passive sign convention, we take the voltage drop along the direction of current through the circuit element. As you can see in the diagram over there, uh, voltage drops along the direction of current in the particular circuit element. Uh, the plus minus direct sign for voltage symbolizes the higher and lower potential, that is a potential difference across the circuit element, and the arrow on the wire represents the direction of current going through it. Okay, so this was all about the sign convention. Now let us see how it applies to our beloved circuit elements, starting with resistors. So resistors is the most simplest of all the circuit elements. It basically works on Ohm's law, that is V equals IR. And as you can see, this is helpful to understand why our sign convention is helpful. In the diagram, you will see IR and VR have been directed. So if you'll see IR when goes through the resistor, we all know that there is going to be a potential drop. So the sign convention aligns with this fact that there is a voltage drop of VR across the resistor R when IR current goes through it, and it follows VR equals IR times R. So talking of power and energy as well at this point, power, as we all know, is I times V. Uh, and from the law, we have power across the resistor, that is I square R times R. And on integrating power with respect to time, we should get the energy. Now, since resistor is a passive element, power will always be positive. That is, it will always absorb power and dissipate energy. So uh, this is because IR and VR will be positive for the resistor, and that's it about the power consumption in the resistor. Coming to the next circuit element, that is capacitor, it works on the basic law of the capacitor, that is Q equals CV, on differentiating the law, you get I is C times dV by dt. Again, passive sign convention for the capacitor, we have IC plus minus VC, and over here, we again deal with the power and energy of the capacitor. So again, let's try to understand it with the passive sign convention. So if Vc is increasing with time, that is dV by dt is positive, then one can understand that on the positive plate of the capacitor, charges are being accumulated. This is possible only when IC is positive, that is I is positive and dV by dt is positive. Hence, our passive sign convention helps us analyze this easily. Again, talking of the power dissipated, or I should say stored in the capacitor, uh, it will be C. Power is C Vc times dV by dt. Energy comes out to be half CV square, and on integrating, we'll get all the required quantities. So, uh, this was about how the capacitor stores energy. Uh, this energy can be drawn out later, of course, because when the capacitor gets discharged, this energy stored in the form of electric fields will be uh, sent to the other circuit elements where it can be used in a different way. Again, as you can see, uh, the power will be absorbed in the capacitor when I and V are both positive, and the capacitor will be delivering power when they are of opposite signs. So IC and VC at this point, I should say that they can be positive or negative as well, depending on whether the capacitor is acting as a power source or it is consuming power. And the final circuit element that, apart from the voltage and current sources, of course, is the inductor. Inductor, again, as we all might know, it works on magnetic energy. So it works on change in flux. So when rate of change of flux is EMF, so from that we get V is L di by dt. So when current across the inductor increases, di by dt will be positive. Since the inductor will try to oppose a change in its flux is L times I, it will try to oppose the change in flux. So it should try to act as a current, so like trying to act as a battery in the opposite direction, so as to uh, stop the change in current. For that, VL, it will try to act as a battery with VL positive. So as you can see, when current increases, VL will be positive, and hence V is L di by dt. On integrating the power to get energy, you'll get that energy is half Li square, and from there one can find the energy and power through the inductor. Next comes the voltage source. The voltage source by definition is a constant voltage source that is irrespective of the current flowing through it. It will provide a constant invariable potential difference of V naught. This is evident in the plot given there, uh, I against V. We have the constant voltage V naught that is delivered, that is uh, even if the current direction changes, the potential difference will remain same. So, okay, uh, again, from this plot, it is clear that, as we discussed from the circuit element so far, that if I and V, according to the sign convention, are of the same sign, that is, let's say in the first quadrant, then the element will be absorbing power, and if they are in opposite direction, that is opposite sign, they'll be delivering power. This is evident from the voltage source, because if V naught is positive, the source will try to, let's say if we have a purely resistive circuit, the source will try to drive power from, drive the current from the high potential to low potential, that is V naught is positive for resistive circuit, then I will be negative, and we all know that this is going to be delivering power to the resistors. So from this plot, it is quite clear that in the quadrants first and three, the that is when I times V is positive, the circuit element will be absorbing power, and in second and fourth quadrant, it will be delivering power. This has been so easy to understand because of the passive sign convention. And this also goes for the constant current source, that is irrespective of the potential drop through it. It will be providing a constant current, uh, and same goes for it. It can absorb or deliver power based on this plot of I against V. Okay, so this has been about the circuit elements, power, and energy. We talked about linearity. Now, there are a few more small bits to talk about. That is the mutual inductor. So, mutual inductor is again uh, two inductors placed close to each other such that the flux going through one inductor is not entirely due to its own current, but also because of the nearby inductor, the field lines of the other inductor will be flowing through it and thus affecting its flux. So in the first case, as you can see that the inductors have been placed and the VI parameters have been labeled according to the passive sign convention, which we discussed recently, and L1, L2 being their inductances, and M being the mutual inductance. So it is evident that V1 is L1 di1 by dt plus M di2 by dt, since V1 will also depend on I2, and so goes for V2. But as you can see, the two sets are different because the direction of current flowing is different. It is same in the second case and the direction is opposite in the first case. So this changes the direct sign of M. We take in this cases, as you can see, it is plus M and minus M. So to avoid the ambiguity in this set of equations, we use the dot convention. That is, if the we you can see the dots placed in the two inductor sets. That is, when current is flowing towards the dot, both currents are flowing towards the dot as in the first case, we take M to be positive, that is we use plus M is positive. This type of coupling is called aiding kind of coupling. Uh, and the second one, you can see minus M has been used, that is currents are flowing such that one is towards the dot, the other is away from it, and this is opposite type of coupling. And here we will take minus M. So this was the dot convention to avoid ambiguity. Now, if we have once labeled the dots and currents, we will have the voltage and current equation, differential equations quite easier, non-ambiguous. That is, the signs of mutual inductances will be clear from this. Now, inductor will be a linear element if its initial conditions are zero, and uh, it is an important principle that one might want to recall here that M12 is M21, that is the mutual inductance of the second inductor in the second inductor due to current in the first inductor, and the inductance in the first one due to the second, due to current flowing through the second inductor. They are equal. This is the principle of reciprocity. That's why the M remains same in both the equations. Okay, and coming to the final part of this is the dependent source. So let me go to it. Dependent sources are basically current sources and voltage sources, but they uh, they they are dependent on the, let's say, on the voltage and current parameters. Voltage measured across some other point in that circuit, let's say, and current going through some other branch in that circuit. So a voltage controlled voltage source VCVS will depend on the voltage Vx at some other part of the circuit and give a potential difference will be that some factor times Vx, we call it K. So it will be acting as a current, a potential constant voltage source with a potential difference K dot Vx. Same goes for I, current control voltage source. So again, we can have a voltage source that is dependent on current, not only on voltage. And here, the potential difference is Rm times Ix, where Rm is known as trans resistance. And we have the current I, which is at some other Ix, that is in some other branch of the circuit. And the potential, as you can see, is some maybe placed in some other part of the circuit, and it depends on that current. That's why dependent sources. And again, we have current sources which can be dependent on voltage and current. Again, uh, the first one here is a voltage control, that is gm times vx against trans conductance, and the second one being just dependent on current, that is cccs, and it gives a constant current k times ix. So this has been all about the circuit elements and their properties. They're basically how they deal, how their voltage current relations, how they deal with energy, how they can store or dissipate energy, and linearity, of course. So in the coming videos, we'll discuss some methods to analyze the circuits. When as of now, we didn't discuss the complete circuits. These have been just elements. In the next video onwards, we'll discuss how to analyze complete circuits. Thank you.